Hello, welcome to the DL Software Digital Guide, a one-stop practical guide for DL software toolkits. This is part of the DLView video series that show you how to make best use of DLView effectively. In this video, I'm going to show you how to set up the force field models for solutions and liquids for DL Poly molecular dynamics calculations. This demonstration assumes you understand the basic operation of DLView software. If you have not run DLView before, I would recommend you to watch the first DLView video titled Ready, Get Set, Go. To set up a liquid or a solution model, you can make use of the Solution Maker feature contained in the DLView control file. First of all, you would need to supply an input file that contains a single unit structure. The single unit can be a single molecule, an atom, or even a group of molecules. DLView will then duplicate this single unit structure according to the parameters specified in the Solution Maker options. Each duplicated structure will be randomly orientated in space. A liquid system model will therefore consist of a number of single unit structures that are randomly orientated in the simulation box. For a solution model, the single unit structures will be considered as the solutes. For the demonstration, we are going to use an ethanoic acid molecule as the single unit structure to set up a liquid and a solution model. The content of the input configuration file is shown here in the simple XYZ format. There are a total of 8 atoms that made up the molecule. The system that we are going to set up is a cubic system of 40 angstrom size and consists of the pure liquid of density 1.05 gram per centimeter cube, which is the standard density of the acid at the room temperature. Now go to the DLView folder. I have placed the ethanoic acid file in the DLView home directory. Let's edit the DLView control file. Change the force field schemes to OPLS. Then change to the correct file name. Next, we will activate the Solution Maker feature by switching from 0 to 1. I have also preset to the desired density of 1.05 gram per centimeter cube. The third parameter, 1.9, is the cutoff distance in Armstrong. This is the minimum distance that is permitted between any two single unit structures during the duplication process. In this case, each ethanoic acid molecule must be separated by at least 1.9 angstrom from one another. Lastly, we will define a cubic system of 40 angstrom. The value 1 for the periodic condition indicates to DLView that this is a cubic system. Let's run DLView. The program reads the XYZ file and calculates the number of molecules, or more precisely, the single unit structures required for duplication based on the simulation box size and the conditions set on the Solution Maker feature. The program duplicates the molecule by going through a series of random translations and orientations. In some cases, multiple attempts were carried out to ensure the newly added molecules are always at least 1.9 angstrom from one another. Now, let's look at the generated DL Poly view file. It shows there are a total of 674 molecules, and this gives a total of 5,392 atoms in the system. In order to view the structure, you can use a third-party program called VMD. To do this, you would need to ensure the number of atoms are displayed in the DL Poly config file. This is the configuration structure of the liquid system displayed by using the VMD program. Notice that the molecular arrangements look a bit ordered, where discretized packing looked vaguely visible. Obviously, the equilibration process would be needed when running the molecular dynamics simulation. Now, I'm going to show you how to set up a solution model. The system consists of two components, the acid molecules as solutes and the water molecules as solvents. We are going to set up a solution with an acid concentration of 1 mole per decimeter cube. Once again, edit the DLFuel control file and change the parameters on the solution maker accordingly. For the cutoff value, we will increase this to 8 angstroms. The way how the molecules distribute in the simulation box depends very much on the cutoff value. In general, the larger the value, the more random and evenly distributed they would be. We will discuss more about the cutoff values in details later in the video. Note also that we are not going to solvate our system at this stage. After the DLFuel conversion, we are going to visually inspect how the molecules are distributed in the system by using the VMD program. Now, let's run DLFuel and see what happens. This is the resulting DLPoly config structure set up by DLFuel. As you can see, the molecules are rather evenly distributed. We will now return to the DLFuel control file to instruct DLFuel to solvate the model. In this example, we are going to use the original TIP3P water model. The value 1.9 was set to ensure the minimum distance between a solute and a solvent molecules must always be at least 1.9 Armstrong. Otherwise, DLFuel will consider two molecules have overlapped with each other and reject the overlapping solvent molecule. Now let's run DLFuel again and see what happens. Visual inspection of the system shows the acid molecules are now being solvated with water molecules. The number of rejected solvent molecules can be found by looking into the DLFuel output file. This information is located somewhere towards the end of the file. Before finishing this video session, I'm going to briefly discuss about choosing a suitable cutoff value for the solution maker feature. Choosing a suitable cutoff value is as a matter of choice and trial and error, and also depends on the number of molecules and the size of the system. Basically, for a liquid or high density system, we need a small cutoff value, typically 1.8 to 2.5 Armstrong. For a dilute solution, the cutoff values can vary a lot, by at least 5 Armstrong or more. The larger the cutoff value, the wider apart the molecules would be from one another. The molecule duplication process can fail if the cutoff value is too large due to too many molecules would need to pack a box size that is not large enough to contain the molecules. When this happens, repeat the DLView program execution, or try a smaller cutoff value. The following diagrams show the duplication of 20 ethanoic acid molecules in a cubic box of 40 Armstrong by using different cutoff values. When setting the value to 2 Armstrongs, the molecules are packed tightly together over a section of the box. Increase the value to 6 Armstrong results in the molecules being more dispersed. Finally, at 10 Armstrongs, the molecules are more randomized and evenly distributed. That's it for this video session. I hope you enjoy and become more familiar what you could do with DLView. Please do explore other DLView videos so that you can learn how to make use of the software more effectively for your work. Thank you and goodbye.